The ventromedial prefrontal cortex and intraparietal sulcus use value information to guide a decision process and carry information about reward expectation. Despite broad interest in the neuromechanisms of decision making, little is known about the comparison process where there are more than two alternatives to choose among. In this study, researchers investigated decisions where the value related to each of several potential options was parametrically varied on each decision so that the interactions between neural representations of several potential choices could be investigated. They extended a biophysical model of decision making which predicts greater difficulty choosing between two options in the presence of a third, very poor alternative, compared model predictions with human choices and neural activity in VM, PFC, and MIP region, explored the relationship between findings and the influential divisive normalization of multi-alternative decision making. Key terms HV high-value options, LV low-value options, D distractor, HV minus LV value differences between the available options, HV plus LV sum of their values, HV minus D value difference between the higher value option and the distractor, HV minus LV times HV minus D is the interaction term.
The biophysical model was developed by Wang et al., and it is used to investigate reward-guided decision-making. A few modifications were made to this model for this study. The overall number of option-specific excitatory pyramidal neuron pools were split into 3 equal populations, with each containing 240 neurons, and a value input was only given to the distractor option for the first 100 milliseconds after the 2 stimuli were shown, while the value inputs of the 2 stimuli were given for 800 milliseconds. Activity and inhibition in neuron pools corresponding to available options were also examined, and model choices were generated once there was a firing difference of 6 Hz between PHV and PLV. There are 21 right-handed subjects, 9 females and 12 males, aged 19 to 34 years, and with no psychiatric or neurological history. In the fMRI task, the stimuli presented were associated with different reward magnitudes and reward probabilities. These were represented by different colors and orientations of rectangular bars. There were 300 trials in total, of which 150 were 2-option trials and 150 were distractor trials. For the behavioral task, the 2-option trial had 2 stimuli shown, surrounded by orange squares. One square turned red as soon as the choice was made. A yellow outline on that choice meant a reward was obtained, and a gray outline meant no reward was obtained. In the distractor trial, there was a third stimulus surrounded by a purple square, indicating that it could not be chosen. The rest of the trial followed the same pattern as the 2-option trial. The image in B shows the different reward magnitudes and probabilities of the stimuli with different colors and orientations. The final reward for each participant was calculated by averaging the outcome of all trials. CAT trials were included to ensure that the subjects paid attention to the distractor. They were interleaved between the decision and interval phase in 15% of the trials, and the subjects had to make a decision within 2 seconds. They made an extra 10 pins with each correct response. The reward magnitude and reward probability were multiplied to calculate the value of each option. Out of all these ways, HV minus D was chosen to report results, as it was thought of as the strongest test of the hypothesis. A logistic regression was performed for every subject to predict accuracy with the regressors listed. Another logistic regression was performed to examine divisive normalization effects on behavior. A Siemens 3T MRI scanner was used to acquire fMRI data. The fMRI-based software library was used to analyze the fMRI data, and pre-processing was performed in 4 ways. A univariate GLM approach was used to do whole brain volume analysis. The MIP and VMPFC signals were extracted from 3 voxel radius spherical masks at coordinates from previous studies of MIP and VMPFC. GLM was also used to analyze time courses. Only matched pairs of trials were included when correct responses were made in both trials. A divisive normalization effect on the COPT signal was investigated using a similar analysis. The relationships between neural signals and different aspects of behavior were examined with the use of partial correlations. A PPI analysis was performed to examine how VMPFC coupled with other brain regions to encode HV-LV and HV-D value differences. Each PPI regressor was generated by multiplying the mean physiological regressor by the mean convolved psychological regressor. A cluster-based threshold was initially used, and then a more stringent cluster-based thresholding criterion was used to reduce the possibility of any false positive results in follow-up analysis.
Researchers extended a biophysical cortical attractor network model to include 3 rather than 2 populations of excitatory pyramidal neurons that represent potential choices as seen in Figure 1a. Each population's neurons receives an input proportional to the value of one option. There was strong recurrent excitation between neurons within populations, but interneuron-mediated inhibition between populations. High-value options are more likely to be chosen by the network because the representative population receives stronger external excitatory inputs. They examined how the comparison between 2 options was affected by the presence of a third alternative in a manner that would generate predictions of behavior and brain activity. If the third alternative has the highest value, then it itself might be selected. They examined the impact of a third option that might be considered a transitorily available distractor. H3 minus D affects the size of the signal representing the key value difference for decision making in the biophysical model, human behavior, and brain activity. H3 minus PLV population difference decreased as distractor value decreased. This effect was more prominent in trials when H3 minus LV was small. PH3 minus PLV signal difference decreased as distractor value decreased. Low value distractors actually lead to less inhibition between populations, which in turn lead to PLV population activity being closer to and sometimes exceeding PH3 population activity during the time period when network activity first makes non-random decisions. This will sometimes lead to LV rather than HV being chosen when the relative value of D is lower. They examined whether D affected whether PHV or PLV entered the higher firing attractor model state. After an initial rise in both populations' activity, the model entered stable attractor state. Analysis of attractor state revealed that the model was more likely to make an erroneous LV choice when D was much lower in value than choosable options. Subjects made more mistakes as H3 minus LV decreased. The same was true when H3 minus D was large. This suggests it was difficult to choose high-value options when the distractor had a much lower value. The interaction term was also significant. The effect of H3 minus D causing inaccurate decisions diminished when H3 minus LV was larger. Subjects were less accurate in the distractor than two-option trials. The H3 minus D effect was only present on distractor and not on two-option trials. The distractor's impact on accuracy is consistent with the predictions of the biophysical model as seen in graph 1G. When D was much lower in value than the choosable options, the model was more likely to make the wrong choice. Consistent with model prediction, the ventromedial prefrontal cortex H3 minus L3 value difference signals were weaker when distractor values were smaller, as seen in Figure 4a. There was no significant effect of the absent distractor on two-option trials, as seen in Figure 4c. An effect in two-option and distractor conditions differed significantly. H3 minus LV signal weakening in the ventromedial prefrontal cortex in distractor trials was thus a consequence of distractor presence. The impact of distractor values on H3 minus LV signals in MIP did not reach significance on either distractor or two-option trials, nor was there any difference between conditions. Distractor impact on accuracy might be mediated by VMPFC rather than parietal cortex. Relationship between the interaction signal and inaccurate behavior was especially strong at late time periods. This suggests that prolonged interaction modulation of VMPFC both led to suboptimal decisions. Individuals who showed stronger reduction over time of the negative signal had higher accuracies. Researchers found a large swathe of lateral orbitofrontal cortex extending into ventrolateral prefrontal cortex to be negatively coupled with VMPFC as a function of H3 minus D. Focusing on the same LOFC region, found an area of positive coupling with VMPFC as a function of the researchers focused on MIP and VMPFC signals co-varying with values of correct choices made with the contralateral hand. MIP contralateral option was significantly diminished as ipsilateral value increased. No such effect was seen in VMPFC. Reaction times increased as IV increased. The interaction term was associated with the negative modulation of the Bode signal, suggesting that IV diminished with the COPT signal seen in 7C below. Across subjects, variation was negatively correlated with reaction time after controlling for accuracy and other neural signals seen in 7D below.
A low alternative value leaves the high and low value potential choices both relatively active, as the subjects are more likely to choose this option. When this third option was of low value, more errors were seen. The average VMPFC GABA concentrations can be measured to test whether less inhibition occurs when distractors have low values. The VMPFC neurons possibly employ more abstract and flexible coding principles than spatially selective IPS neurons, suggesting the fundamental difference in decision-making mechanisms between the VMPFC and IPS. Failures of optimal decision making could be further explained by understanding the influence of situational variables favoring either parietal or VMPFC control of behavior. This could help determine patterns of deviation from optimal decision making. The nature of the VMPFC decision-making mechanism may cause failure of optimal choice in some circumstances. Contralateral chosen value signal was specific to one response side, and its size was reduced in proportion to the value of alternatives on the other response side, as was predicted by divisive normalization accounts. The IPS and VMPFC constitute two components of a system for value-based choice, but this suggests that both components might simultaneously attempt to select the course of behavior. To identify a normalizing effect of stimuli presented in different quadrants in the same hemifield as the chosen option, behavioral tasks requiring more spatially resolved responses and more spatially resolved brain signal recording might be necessary. Biophysical models of other brain networks can also be studied to find if there are similar activity patterns to those observed in the parietal cortex.